Good evening.
Good evening,
Good
sir.
evening.
Okay, thank you. Let me start. Second. So we still have a couple of homeworks, right? So we still have homework 3, SQL quiz, fraud detection in Python quiz, and time series by April 20. So please let me know if you have any questions, outside the, maybe we can use the last 10 minutes. Let's see if we have time. Otherwise, if you have any questions, please let me know. Just one thing, which is in homework 3, I think. I received this question. Okay, let me show my screen actually first. Okay. So I received this question about question 4. I received this question twice, fraud detection. So you can see each one of them, there is links for each one of the questions. Question 4 is separate, as a 3 is separate, 2 is separate. So each one of them should be considered as a separate question. So fraud detection as an example of anomaly detection, blah, blah, blah. And then you open this, the instructions, it says, read up to this section, which means, just copy paste. Control F. I don't know why it's not showing. Maybe it should be refreshed as I'm scrolling down. Strange. Okay. Let me double check this part. Maybe I was looking to the cached version of this web page in my machine. Okay. Okay, but let me double check this part. But there is this part about chapter 1. The data set is in chapter 1, which is chapter 1. It's at the top here. You click chapter 1. You see it's almost at the top. So you click chapter 1. And yeah, you can see it's downloaded. You see, I just click chapter 1. I can see the data. And then I gave you some instructions about the structure of the data. So, for example, can be installed and search for chapter 1, and then you create folder, call it, call data, call the folder data and the same directory. And then, it's not hard. The idea is that the code here is written to point to chapter 1. See, it's referring to chapter 1. So make your own magic to make the path refer to chapter 1, and we need to be able to read these files. That's it. Simply do it in your own way. But yeah, if something is not working, please let me know. I get 2 questions only, which means, I don't know if you guys have started or still waiting to start working this project. I know there's 6 days left, but I prefer if you guys can work earlier. Yeah, so please let me know if you have any questions about homework 3. The quizzes, be careful when you work on the quizzes. Some of them are multi-answer. You can tell your graduate students, you can tell that there is square, not circle. So if it's square, there is a chance that it's a multiple choice, multiple answer question. When it is circle, as you know, it's multiple choice. So be careful about these things. So so if you are getting some grades, whatever, you might get a grade like, for example, 3.5, because I have partial credits, for you. So if you get, let's say, suppose the question in the quiz, to get full mark in any of the questions, you need to, provide 2 answers. If you get one of them correct, you still get partial credit. You will not get 0. So
I didn't pay attention.
nice. So
I
that's what.
realized it actually, but it didn't
My my
mention.
my score was really bad, so
Yeah,
You have more
mine too,
homeworks,
actually.
don't worry. I think we have how many? We will have one more quiz at least. So yeah, we have two quizzes so far. Yeah, we will have one more. I will try to have maybe two more because we have 20, so each one of them will be 5% of the total grade. Let's see. Let's see. Yeah. So I may drop the lowest grade. Let me think about it. But so far, I'm planning to have one more question, one more quiz about today's material, definitely. And today's material also, since we have done project phase one, we will have project phase two is related to today's class. So two things out of today's class, project phase two by the end of the semester, and then one more quiz at least. Yeah, so, and I think we get four homeworks so far. In terms of homeworks, we are, I think we have good coverage over there. Discussion, definitely we'll have one more discussion as well. So yeah, discussions are easy. I think you guys are doing good here. But for the quizzes, I know some of the grades are not that very fancy, so I may drop one of the grades in the quizzes. Let me see. Or I give it as bonus, maybe, that whatever the grade for that quiz, I may add it to your total grade and that's it, without dropping any grades. So let me think about it. I mean, it's good to have a full picture about the grades, then we talk about, I can think about it better. So today's class is, uh, p- you know, eh, people take it, so it's about regression. Actually, regression by itself is a very big topic. It's not is not very simple. Is not as easy as you think. Um, there is, I think this book, if it's not in Canvas, but since today we're starting, so there's books only about data analysis using regression. So this book is very good book. You can take a look to. If it's not in, I will double check. If it's not in Canvas, I will put it in Canvas, upload it to Canvas. Um, you know, regression is there since tens of years. It's in mathematics, and people like it and continue to use it because it's working. Why we need to come up with, and new mathematical models, that may not work or may not be comparable as linear regression. People like it because they can interpret regression easy. So when you take a look to this book, try to take a look, consider reading at least, up to chapter 3 and 4. Sorry, up to chapter 3 and 4. For your own knowledge or for your reference. It's really good chapters. If you want to do something little bit fancier, we have seen before the classification. Logistic regression is one of the models that's used for classification. So if you understand the linear regression, you can just add little bit info about logistic regression. And the difference in logistic regression, it will give you a predicted value between, -1 and 1, and sorry, between 0 and 1. And in this case, anything below zero point 0.5, you can call it class A. Anything more than zero point 0.5, if it's predicted more than zero point 0.5, you can call it class B. So at the end of the day, it is used for, classification. It's really nice. It has some overlapping metrics with regression. So you are adding just little bit knowledge, in the top of linear regression, and this way you understand logistic regression. It's very popular. Where I work full time, we have a team who's working only in logistic regression, days and nights, improving this model, over different versions. We have another team who's working with linear regression, days and nights, and they are trying bunch of methods that I will talk about it, how to improve the linear regression. So these models, like I said, even though, I mean, if you Google about machine learning models or mathematical models that can be used, you will see, tons of them. There is, for example, people talk about having, XGBoost regression, which is part of what we call tree models. There is XGBoost models, people try to use, uh, you know, Lasso. ridge as a variations of linear regressions to make it, to improve it. Sorry, to get another variation because of the nature of the data. Linear regression, we are investigating a linear relationship. We are trying to find a linear relationship, where others, they might capture, a non-linear relationship. There is a plenty of tree, what they call tree based models. So this is the family tree. So we have a regression family, and then we have tree based models. But people, like I said, my team, where I work, that we are three teams so far, and one of them is only working with linear regression days and night. The other team is working with logistic regression, and the other team, they are doing analysis using different analytical tools and based on different requirements. So linear regression, but it's very important, not to rely on, for example, go to R, get, implement it, and that's it. Go to, for example, to Python, import whatever that library, and then just write 2 lines of code, and then you will get the linear regression, the equation of the linear regression. It's important, if you go to YouTube, let me show you. Actually, in the previous semesters, I used to have it as part of a part of the class, where I ask the students, to I work the students over the derivation of the equations. But let me share it with you. Just 1 second. So it's really nice. It's really nice to understand how. Okay. Let me double check this video before I share it with you. 1 second. Yeah, I just remember that I should have it. Yeah, I think this is one of them. So this is a simple example. It's showing you a couple of points, A, B, C, D. They are in the XYZ coordinates, and as XY coordinates. And this A or B or C or D, think about it, if you have 2 data points, think about it. If you have X and you're trying to predict Y. Okay, so for example, if you have the heights of the students in any class, and you are trying to predict the height of a new student. Okay, so you're trying to predict the height of a new student. So you want to build the relationship. So the height and the age. I'm sorry. Let me show you something. Maybe it's easier to have it in Excel sheet. I have, oh, not this one. I'm sorry. Yeah, this one, for example. So this is an example. You can see this is a data set that has first name, last name, blood type, marriage status, and income, and then device, whatever phone they are using. So imagine if you want, let me insert this. So imagine if you have this case where you want to use, maybe, let's see, maybe Android device, okay, to predict the income. So you will call this X, and you will call this Y. If you feel it's vague, let me add one more column, call it age, maybe. And this age, just let's say 20, 30, whatever, 22, 15, something like this. Suppose you want to use X, you want to use the age of a person to predict their income. So you will get 2 points, right? So so you have X and you want to predict Y. So if you want to, represent this in XY coordinate, you will use X and 100, sorry, what is it? 140K. So your point in the x-axis will look like this, 20, 145K. This is as we know it, this is how we know it, X and Y. But this is the simplest version of a linear regression where you have the points this way. So you have x, you want to predict y, or you have x, or you predict y. You can flip them, you know. So that's 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 why I'm saying, you know, these are in xy coordinate. So x is used to predict y. X is used to predict y. So now the idea of the linear regression is to find, you know, the best line that can fit all these data points, you know, with a minimal error. What does it mean, error? So the distance between the line and the point, we call it the error. So this is for B, for example, is the distance from the matching point here on the line and B, we call it error. So you can see C has the minimal error. A has a little bit more error. B has more error. D has more error if you extend this line. So the idea is to find, you know, something like, you know, okay, what is the best line? You can see they're trying to come up with different lines. But then at the end of the day, okay, you know, what to do. So you are going to use this data to find the best line by applying some mathematical equations. From where you will get this equation? This is by, it's given by the person who built this, you know, machine learning model, or sorry, mathematical model. So yeah, you can see that, you know, they start with these equations and they try to continue the derivation with some data. I will find better example for you that shows the data set at the beginning, so you can I think this guy, there's some videos that show you the data set and how they are using the data set. So how they are using X and Y. Like I said, in previous semesters, you know, I was doing the calculations in the class for the students to get X and Y, but I felt it's better to talk more about what's after getting the equation, because there is plenty of tools that can get you this equation, and I leave the videos to the students to watch it, you know, and find you know, find out how we can get. Yeah, this is one of the points. For example, say this is, they're trying to give you some points and try to explain the logic behind linear regression. So some of these videos that I'm talking about, you know, here they are not paying attention to any values. You know, they are just computing, they are deriving the equations, and then they will be using the equations. So at the end of the day, you know how to compute the coefficient in any linear regression. It is at the end, which is A1 and B1. So if you notice, if you Google, um, let me show you something here. If you type linear regression, as you know, at the end of the day, after working with any linear regression model, you need to end up having an equation, y equal p0 plus p1 plus x. So in this video, p0 or p1, it is what he's trying to calculate here. This is what he's trying to calculate. So sometimes they use x0 or x naught, they call it, and x1. They're trying to derive, you know, show you at the end, you know, what are the values that you should be computing. I'll try to find my file from previous semesters if I find it, because I spent too much time honestly developing that file. But otherwise, if I didn't find it, I will try to find the video that has a data set showing, you know, how they derive this and share it with you guys. So, okay, so linear regression, again, let's go back to this example. You know, we have this example. Let me have it next to me. So again, think about it. We wanted to have or build a linear regression model in the simplest format. I want to use X to predict Y. I want to use the age to predict the income. You know, and for that, I want to use, let's say, you know, linear regression. So what is linear regression then? It's definitely it's a statistical technique. Now people, they call it machine learning technique. Now, because it's implemented in Python or whatever, they start to call it machine learning, but actually it is nothing but a statistical technique or mathematical technique that's used to find a relationship between dependent and, you know, independent, one or more independent variables. So what does it mean dependent? What does it mean independent? Let me just keep this. Okay. So the let's pay attention to my question. So I want to use X to predict Y. So Y values, it is similar. It's kind of, I'm saying I want to use x so to predict y values given that I know x values. So y in this case, it's a dependent variable. It's a dependent variable. It depends on x or more of x's. It's not just one feature. And this simplest example, I'm using only age to predict y. I could use, for example, height. I could use maybe, years of experience, for example, to predict the income. So only in this example, I'm only using age. So, and all the time I'm in linear regression or regression models, I'm trying to predict only one dependent variable. One dependent variable. Now there is techniques, where you can have, predict multiple values from the same input. This is an implementation. This is a way of implementing these techniques. But so for example, you can predict three values. One is, let's say, for income, one for whatever, but using the same input features. So in our case, our input feature is age. We are trying to predict the income. Income is the dependent variable. That's why I said here one or more independent variables. X, it does not depend on anything. Why, if there is another X, it does not depend, it shouldn't be dependent on anything. So the relationship between all the X's, let's say, either years of experience or age, they shouldn't be dependent on each other or on any other variables. They should be independent. They should be independent. So, which means if you have two variables in the X set, okay, in X set, the independent variables, we call them the X set. If you have dependency among these variables, you should keep only one of them. You cannot keep both of them if you want your results to be accurate. If you want your results to be accurate, you should keep only one variable. If you in X set, if you have two of them or more that they depend on each other. So again, dependent variable is y, independent variables is the X set. In our example here, we have only one variable in X set, which is called age. So an example, imagine you want to predict house prices. The price is the dependent. You want to predict the price of the house. What you want to predict is the dependent variable. But this could be influenced by factors. These factors, we call them independent variables or the X set. What could be, for example, the size of the house in terms of square feet, maybe the number of bedrooms, maybe the lot size, maybe the number of restrooms, maybe the location, the address. So there might be other variables, that is used to predict the house prices. So these variables that we consider when we try to predict the price of the house, we call them independent variables or X set. Another example, like I said, this is very popular example, which is the age and income and years of experience. If you want to predict the income, um, it's a dependent variable. We saw before an example earlier in this semester about the parents and the heights of their children. So parents' height and children height, which means, if your dad is tall, you are expected to be tall. So we have seen this example before. So in our case, if you are trying to predict the child height is dependent. The parent height is independent. So at the end of the day, what we want to get from the linear regression, we want to get a linear equation, right? We want to get a linear equation, and that linear equation um, uh, should be used to predict future observations. Today, for example, let me show you something here. So let's take a look to this. So in this case, if you see all these blue dots, these blue dots represent what data we have on hand as of today. What data we have on hand as of today. So we want to fit a linear line, okay? that linear line represent a linear relationship between x and y, and we will be using this line, or we will be using the equation. See, this is the equation. So after you get the line between these orange dots, for example, you will get an equation. So once you get the equation, we want to use that line equation to predict future observations, to predict future values. Okay, so we will be using the equation of this line again to predict the value, the future values, the future values. What we are going to predict in the future, the value will come to us in the form of x value, because we are talking about simple model x and y. So we will get x value. We will be using x to predict y, or to calculate y, to calculate y. In this case, if I get the value as 30, if I know the equation, I will feed 30 to the equation. I should get a point maybe somewhere here. So this point will be my predicted y value slash computed y value, slash computed y value. So that's why we're saying, linear regression helps you figure out the equation of a straight line that best fit the data points, best fit the data points. It's, it's a mistake if you are saying, that fits. Many lines that can fit, but you need the best fit. Like I said before, the best fit is the line that minimizes the error. That minimizes the error. Like I said, what is the error? The error is the distance between the actual point and the line. Because the dot, the corresponding point on the line is the predicted y value. The blue dot here is the actual. So the difference between the actual point and the predicted point is what we call the error. So we want to have a line somehow in any direction, 45 degree, maybe 60 degree, 70 degree, 35 degree, that best fit, which means, that has the minimum, or that can cause the minimal error. There is two types of linear regression. If we have the simplest format, we call it simple linear regression, where we have only one independent variable. If we have more than, if we have two or more, we call it multiple linear regression. We call it multiple linear regression. Okay. Now, as you can see in the left side, once you compute the linear regression equation, let me show you something. Actually, I have R file here. Let me see what it is. Let me show you something here in R. So see, this is a linear regression formula between, we have three variables. We have three independent variables: weight, clarity, color, and we are trying to predict a value. Okay. This example is simply, this is what's called, the diamonds data set. So if you are going to buy a diamond from jewelry store, the value of that diamond is estimated based on the weight of the diamond, the clarity of the diamond, how clear is it, and the color of the diamond. So for that, in this example, you see this is this code in R. So this is linear, regression model, and it's the equation for that. We're trying to see if this is a good model or no. So we're trying to predict the value. C tilde means, to differentiate between y, which is our value, and the x set. The highlighted three variables are the x set. Okay, weight, clarity, and color. Now, as you can see, I don't want to talk about right now. I mean, we will come back to this example shortly, but I want to share something. CR, after you get this computed, R gives you these three stars. Sometimes could be 2 stars, sometimes could be nothing, sometimes 1 star, sometimes 2 stars, sometimes 3 stars, sometimes nothing. Okay, this is what you see here. I'm having the significant code. Okay. Um, what does it mean? So the 3 stars, when you see the 3 stars, This means that the p-value, as you can see here, ranges from 0 to 0.001, which means that variable, that feature, is highly or very highly significant. What does it mean? For example, for predicting the value of the diamond, you can see weight and clarity have 3 stars. This is telling me that these two variables are very highly significant, which means they are key factors based on the data on deciding the value of the diamond. These two are very highly significant features that I should keep in my machine learning model or my linear regression model. In the case of color, you can see we see nothing. Okay, there is nothing. This is telling me that the p-value for this, it's between 0.0 to 1. You can see it's in the table as well, here in the back, 0.0, 0.1, sorry, to 1. What does this mean? This is telling us that color is not significant at all. So when you have no stars, this means it is not significant. When you have a 3 stars, which is the maximum, this means it's very highly significant feature you should keep in your machine learning model. Now, if you have, let's say, 2 stars, this means, it's highly significant. If you have 1 star, this means it is significant. If you have dot, see, there's option dot, you know, it means, it's marginally significant. Okay. So for this case, for the case we have here, for the example, we have color because it's insignificant. If you take it out of the model, if you take it out of your machine learning model, you will not see any impact on the errors. You will not see any impact on the residual standard error. So this is kind of one of the criteria we use to evaluate the linear regression model. So taking out insignificant feature shouldn't have any impact on the model performance. For example, adjusted R square is one of the metrics, so that you can see this one, if it is higher, this means it is good. If it's lower, this means it is not good. In our case, it's not good that much. It's moderate. Usually people look at least, for 87, 0.87 or 0.85 and more, because what does it mean, adjusted R square? Means, it's kind of describing, or think about it, is the level that your model or your linear regression model is capturing the relationship between X and Y. So if you say 90, this means, kind of, with 90% of confidence, we can see that, we can say that your linear regression model is capturing 90% of the variations between X and Y. Okay, variation means the relationship. Think about it. If it is 62 or 63, in this case 0.63, this is telling me that this model is only capturing almost 63% of the variation, which is bad. Think about it. If you only understand 60% of an article you are reading, which means, you didn't get any, almost you get nothing from the article. But if you understand an article, let's say with 100%, you can say, I'm confident I understood the article. Similar thing, here for adjusted R square. It means, that your model is capturing the relationship between X and Y with that number. If it is more than 85, 90, let's say, this means, it's really your model or your linear regression model is doing something great by capturing this relationship. In our case, for example, 0.63 is almost nothing, so it's not very good, model. What we can do, I mean, there is a few things we can talk about it later. So that's why I'm trying to bring the significance code. We have general principles. Now, there's some some general principles that is used sometimes. I mean, we use them all the time, sorry, with linear regression models, and it is related to the significance code. At the beginning, when you start working with linear regression, try to include all the input variables. So for example, if you have, in this case, I have, as you can see in this example, I have first name, last name. Definitely these shouldn't be part of any machine learning model, but I have blood type, marriage status, device, I have age. I want to predict, think about all these as X. Let's make it merge and center here. So imagine if this is the X set and this is the Y I have, and I want to use all these four variables to predict income. So when I start, if this is, if I have it, suppose my data set is 100 feature, I should start by using all this 100 feature. So the logic here is don't start to pick. For example, you get this data set. Oh, let me see. Okay, what is the blood type is going to do for the income? What is the importance of being married or not to your income? How it's going to impact? Okay, I think I'm going to ignore, for example, marriage status. Don't do that. Don't use your personal judgment on any feature. Don't use your own personal knowledge. Always start by, you know, including all the input variables, all the X set. Okay, that you might be expected. Now, from where it's coming, might be expected. This is coming from the domain knowledge. Don't use your own knowledge. Try to use, your domain knowledge. For example, I know for sure, if you are, the marriage status could have impact in your in your income. Why? Because, for example, some articles, the person who gave you the data set told you, combined income between, the husband and wife will increase the income of the family. Then this means the income should be higher. So we are expecting married to have higher income. A device, if you have maybe a device could tell, for example, if you have Android OS, if you have Mac OS, whatever device you own, this might have an impact in your income. Maybe blood type. Oh, maybe it doesn't have any impact. But the idea is try to use the domain knowledge understanding to include, a specifics. Start with all the features that you suspect that they might bring some importance to the linear regression model. It's not always necessary to include these inputs as a separate predictors. For example, sometimes the inputs can be average or some to create total score. Yeah, so the idea here, sometimes, you don't, sometimes, you might think about a way to combine two variables together. Okay, if you guys remember last homework where I asked you to find the relationship as x equal y, whatever, last homework. In that homework, you don't need, if you remember, some of you gave me a relationship between three variables. If you add them or subtract them somehow, you will get the fourth one. So in this case, you need, as either you keep these three, the separate three by themselves, and you drop the total from the linear regression feature set, or if you are fitting a linear regression, or you keep the total and you take out the three. Why? Because there is a dependency relationship. There is a 100 dependency or highly correlated dependency. There is highly correlated relationship between these three or four variables with the total. So either you keep the four or you keep the total, but don't keep both of them. Why? If you remember, I said in slide number one, they should be independent. They should be independent. So if there is dependency, we should keep one of them, not all of them. Um, so in general, once you start seeing these stars or the significance code, you try to judge them. After you start, like I said, you start with all the variables that you suspect that they will bring some importance to your machine linear regression model. And then you start, dropping some of them, keeping some of them. But before you start dropping them or keeping some of them, think about it. How you think about it, there is some guidelines. This is not like a religion, just think about them. You just keep them in your mind while you are looking to the future. If a predictor is not statistically significant and has the expected sign, what does it mean by sign? You can see here, this is, for example, clarity positive, weight positive, color negative. So the sign is negative. The sign is positive. The sign is positive. So if you are expecting, for example, the darker, the color, the cheaper, the diamond, if you know this as let's say as an expert in the diamond domain, then the advice for you here, is generally, what is it? It is generally fine to keep it. Okay, it may not help in the predictions definitely, but maybe it will not hurt. So in our case, for example, if we are a domain expert and we know for sure if the color of the diamond is as dark as the color of the diamond, you know, uh, um, um, uh, as the price will go down, if we know this for sure, then negative sign is, is a true sign. So even though it's not significant, it doesn't hurt. This is what I said before. If you keep it or take it off, it will not bring any impact. But it's fine to keep it. It's fine to keep it as part of your model. If the predictor, so now you understand the sign. So if a predictor is not statistically significant and it does not have the expected sign, definitely this should go away. The same here. For example, if you know the color, should have a positive sign. Okay, so it's not significant, and this negative sign is wrong. If we know that it is wrong because we are domain experts, then I should drop it from the model because it's gonna impact the model predictions. If a predictor is sorry, it's not gonna impact the model predictions. It's gonna impact the model interpretation. If a predictor is significant, as the 3 stars we have for weight and clarity, you can see 3 stars. If a predictor is statistically significant and does not have the expected sign, so it is significant, but for some reason the data is giving us the opposite sign, as we know. So then you have to think about it, what has caused that feature to get negative sign or positive sign. For example, if I'm expecting weight to give me a positive sign and I found out that it is negative sign, this is an indication of what we call lurking variables. So lurking variables means there might be some other variables or features from the X set you may have not considered. So try to add additional features from the X set to the model, and hopefully this will invert the sign of the weight. Instead of positive, it will become negative if you are expecting that to be negative. If you're expecting to be positive and you get it negative, this means this is a sign. Again, this is significant, and you are getting the opposite sign as expected. This is an indication of what? It's an indication of lurking variables, which means there is a variable that's missing. Okay, and you should go back and look at the input features you have. If the predictor is statistically significant and has the expected sign, as we know, for example, we know a diamond is sold by weight and clarity, and nicely we have these two significant and they have the expected sign, definitely without any further thinking, we should keep it in the model. So these are guidelines, what to keep and what not to keep in your model, and how to think about the variables when you get them, with respect to the significance code. Linear transformation, sometimes, the model does not, is not good as we want them. So, so what we do, let's see this one. I have an example. 1 second, let me find it out. All the examples I'm showing, it's in the slides. The links are in the slides. So for example, take a look to this website. This one, the link of this is in the website, in the slides. Take a look to this one. This one, they are trying to predict the brain weight using the body weight. Okay, trying to predict brain weight using the body weight. The model is giving us residual errors, residual standard errors at 300. Excuse me, as 334. Okay, so what should we do in this case? This is very high. Even though the adjusted R square is 0.87, this is good number, but still the residual standard error is a little bit high. So what should we do? There is multiple options for us. As we will see in this slide and the next slide, we can start with doing whatever. For example, we have linear transformation. Linear transformation, we have seen this before with z-score. It doesn't have any impact on the fitting, but at least they will not impact the predictions, but they might impact the interpretability. For example, uh, what is it? R. Yeah. So sometimes, with if the values you are trying to work with is very high, you might end up having, this one in thousands. For example, imagine clarity is, let's say, somebody income per year. So you will have two big values here to talk about. In terms of interpretability, you might end up having, big values here and small values here. So in terms of interpretability, it's better to have linear transformation to bring them down to certain range, to make it easy, to make the interpretation easier. It does not linear transformation. If you remember, we have seen this with Z-score. We have seen this with Z-score when I showed you the histogram before and after. No impact, no impact at all, except showing you nicer coefficients that you can talk about. That's it. In terms of, remember, with the histogram, if you have big gaps in the y axis, where you can see where your value range starts from, let's say, 0 to 100 million, something like this, if we're talking about countries population. So it's nice to have, to transform for example, the number of people, the population size to be between, let's say, 0 and 10 or 0 and 1. Why? Because it will, my y-axis will look nicer when it is between 0 and 1. How I can do that? I mean, I can use these scores. I can use the min-max. But if I use population, size in a linear regression model as it, or I feed it to a transformation, then I use the transformed values. Is there any impact in the model? No. But keep in mind, if the values you are working with, like population side, they are in millions. Think about it. Linear regression model is about calculations. It's mathematical calculations. If you use the transformed values, it will become, the calculations will become, I mean, it will be with smaller values versus, keeping the actual values. Imagine if you have the population size in millions, and all the equations that you are working with, it will end up 3 million multiplied by 2 million multiply whatever. But if you change this to a smaller range between 0 and 10, all the values that are used in the calculations for the predicted values, it will be with smaller range, like 7 multiplied by 10 multiply whatever. So you will not run out of memory issue. And you can see the big difference. You can see, for example, here, this is how the parent, this is the parent child, you know, uh, I think this is the height in inches. I think this is the height in inches, if I remember correctly, this example. You can see here the parent data is 70, between 60.68, 65, 64. But see the transformed value. If you use the scale function in R, you will end up having 1.2. So 1.2 corresponds to what? To 70. See, it's big. It's a big difference. But is there an impact in the model, improving the model? Keep in mind, no. Okay. Um, there is other methods you can use, centering and standardizing, especially with models with interactions. At the beginning, we will talk about, two things here, or three things. Um, what is center and centering by subtracting the mean? It is straightforward. Uh, let me show you an example. So I have another one, I think. Yeah. So for example, here, as you can see, what you can do, for example, I want to center and scale. Let me just show you the slide. So the slide is saying, sorry, it's saying centering by subtracting the mean of the data. Okay, how I do it? I visit every single variable by itself. So for example, diamond, I have the diamond data set. I have the weight variable, the weight feature. So what I'm gonna do is I'm gonna subtract every single value in weight. Sorry, I will subtract the mean of the weight column from every single value in weight. Okay, so again, think about it. If the average is, let's say, for of the weight is, let's say, 7 grams. So what I'm gonna do, I'm gonna subtract every single diamond weight or sorry, subtract the mean from every single diamond weight. So that's called, centering by subtracting the mean of the data. And if you can notice, if you see here, is this bringing any benefit to me? Definitely. There's, let me show you. Um, so this is normalization using minimum and maximum. As you can see, the model is performing. Let me double check this. Yeah, see the residual error, for example, if you subtract the mean. Oh no, I'm sorry, I just uncommented this part. Yeah, I don't have an example here, but we can test. See the impact of this. I will give you this R code so you can play with it. So you just uncomment this part. It was commented. Just uncomment this one, line 80. And it is the same as the title in the slide. And you will see the impact of centering by subtracting the mean of the data. Now, again, these are options for you. Okay, you don't need to say, okay, I'm gonna use this if I have this case. You try all of them. There is another method, for example, scaling by 2 standard deviation. So this one, for example, let me show you. So there is a research paper about it. Actually, it's called scaling regression inputs by dividing by 2 standard deviation. Okay, scaling regression inputs by dividing by 2 standard, deviation. So if you read this article, I left it for you. This is one of the ways to do what? Centering and standardizing. Now, this is the link of the article. And if you take a look to this, if you read this article, you will see that this article, talk about, scaling regression inputs to make the regression coefficients, at least more interpretable. Okay. And what does it do here? What we are doing? It's very simple. It's, dividing each numerical variable, because, we're talking about dividing. So it should be a numerical variable by 2 times the standard deviations the of that column or that feature. Um, so the author, Andrew, in his research paper, claims that this method or this approach, should help improve, the linear regression model. And you'll see it's very short one, and you can see there is some examples here. He's talking about some examples. Yeah, and he's discussing that example. So it's very straightforward PDF paper. Another transformations we have logarithmic transformation. Honestly, the other team, I don't work with them directly, but they are using this most of the time. Why? Because there is a big reason why you need to use logarithmic transformation. It is to reduce what? Reduce skewness of a variable. So if you have variable that's skewed, if you need to reduce the skewness, you should start with, with transformations. So we know for logarithmic transformation, we have a reason why we're using them. If we want to reduce the skewness, and I want to show you something about it as an example. This article that you saw in the slide, the link is here in the slide. If you can see the body weight, so the body weight, the skewness, let me see. This should be. Uh, just a second. Yeah. So let's see. So you can see the skewness of this body weight and the brain weight. You can see these are the skewness scores. And we can tell from the visualization. This is the body weight. You can see this is the right skewed data. This is the same right skewed data. This is brain weight. This is body weight. And if you just fit them in the model. This is a very simple machine learning model, so linear regression model. This is trying to predict brain weight using the body weight. Okay, and as you can see, this is the model we got. Body weight looks like a significant feature, but there's something to note. Yes, this value is good, but there's something to note. That is the residual standard error is a little bit high, 334. So because why this could be, you know, why could be high? That's why it's important. If you remember at the beginning of this course, we started with working with EDA, the explanatory data analysis, to see how the distribution of each variable looks like. So because I have that big standard error, I should take a look to the distribution. This is right skewed. So I have skewed variables or skewed features. What the author did here, the author is just applied log transformations. You can see this is log transformation to both sides. If you notice what happened, the adjusted R square almost stayed the same, 0.87, 0.86. Not that much of difference, but where's the difference? It's in the residual errors. It's in the residual errors. As you can see, the conclusion is our error decreased to 0.79. That's really much better than the previous model. So if you notice, if you take a look to this example, you will see the only difference is that there is no log transformation. There is no log transformation. The problem here is the error is high, the error high, and see here again, they are saying maybe, keep this in mind. This transformation is something to try, not something to say, okay, if I have this case, I'm gonna use this. All the time, there is multiple options for you. Just try which one of them will give you better results. There's no strict rule which one of them will be the best for your case. Square root transformation, instead of, you can take, instead of using the log, you can use the square root of the feature. For example, here in this example, instead of using log, just use square root. Maybe square root, maybe cubic root. You can try any of these root transformations and see if it's gonna, solve the problem in your linear regression model. Finally, when you have two regression models, so when this is a question I want to give a bonus for. Why or how you will end up having multiple linear regression model? So why you could have multiple linear regression models for the same data set? Is there a way you could have multiple linear regression models for the same data set, or what? You remember before we started this class, this session, saying that you you will start by a feature set, right? And this fee or input set or X set, you will think about the features that you think based on your knowledge or your domain knowledge that okay, these three features might be a good features for a machine for linear regression model, or maybe the other features, maybe this feature and that one. We have seen a case where we might have a case of lurking variables, so we took out a feature, but then because you are getting a negative sign, maybe you need to add it again. So by trial and error, you will end up having multiple linear regression models, and they might give you close R square, and then you might end up having very close error. But at the end of the day, you might end up saying, okay, why not to do final thing, final touch. My final touch that I'm going to add is to compare these regression models using ANOVA. So in this article, compare linear regression models, it is showing you how to compare, multiple linear regression models. As you can see, for example, here, the same diamond set. This is a model that uses only weight as a feature. This model uses weight and clarity as a feature. And this model uses weight, color, and clarity. So we have three models to predict the diamond price or the diamond value. And in this model, um, And we can see here is very simply in R, you can just call ANOVA and you add the name of the first model, the name of the second model, and let ANOVA do the analysis for you. Okay. And as you can see, the degree of freedom, the interpretation is below, but one thing we should pay attention to, which is the p-value. As you can see, the p-value is very small. You can see the p-value is very small, which means, it is telling us that the adding clarity, because what is the difference between weight and clarity? So adding clarity, did lead to a significantly improved model, right? So, which means, in this case, model 2 is more significant. Model 2 is more significant than model 1, or model 2 is better than model 1. Let's see adding color. So what we need to compare, model 2 and model 3. So what is the difference between 2 and 3? As we said, color. And if you remember, color was not significant. So comparing 2 and 3, you will see that we have, where is it here? 2 and 3, we have these two models, and, we are seeing that this p-value, which means 2 and 3, they are not significant. So adding, adding color, is not bringing any significance to, to the model. That's why you're saying, we should reject model 3. So you're comparing 3 to 2, comparing 3 or 2 to 3, let's say. So because of this p-value, this is telling us that adding color is not bringing any additional value to the model. Okay? And so on. So this is a very simple article you can read about, and they have it in the slides. So yeah, I want to stop here and see if you guys have any questions. If not, like I said, expect one quiz, at least one discussion, and we still have one more session in April 28th, I think, Monday, April 28th. And then, yeah, you should expect project phase 2 as well. These are, I think, the last assignments. So 3 assignments will be. Any questions?
I have question about homework 3. Question 1 through 4, each one is independent.
Everything is
So
independent, yeah.
yes, when we report, do we need to create report for each one in
No. One file.
one
One
file
file.
for each
One
one?
file. If you want to make separate, I've seen students, they make separate files. It's fine, but it's up to you.
You also want a code, code.
If it's asking for code, yes.
Code is gonna be, yes,
Is it asking
separate.
for code? No, code. See, if it's now, see, some students, I like the way they are doing. They are submitting if they build the solution in coding from A to Z, they convert the notebook to PDF and they submit it with every answer and as notes and comments, which is really great. It's fine. If it's asking for code, yeah. So for example, in question 2, I'm asking you explicitly submit a commented working code with the dataset. So this means, you need to provide code that I can run if I want to run. If I try to run your code or I suspect that the code is not working, and I ask you, I'm expecting you to send me a Python file of the screenshot of the code that you send me, because some students may end up sending, let's say, a screenshot of their code. But if I wanted the real code, you should be ready to send me the code. Question 1 is asking you read and implement the following code. So there should be a code. Okay, there should be a code that I can execute and run if I want to. Yeah. And again, question 3 is again about implementing. So I'm fine with notebooks converted to PDF and all the solution in that notebook. If you want to convert them to PDF, I'm fine too. It's up to you. Separate files, one file, again, it's up to you.
Okay, thank you.
Yeah, no problem. Okay, thank you so much, everyone, and have a good evening. Bye-bye.
Bye.
Bye.
Bye.